Hello, welcome back. Today we are going to be taking a look at Lesson 5, Gas Stoichiometry. From this day forward, I'm going to be looking at different variations of stoichiometry. So we first covered gravimetric, which had to do with the mass, and today we're going to talk about gas. Let's go ahead and review our Stoic skills before we move forward. What you're going to notice is the method is the same. What we use for unit analysis depends on what is given to us. So I'm going to go ahead and do this problem. If you like, pause, and then you can unpause and check your answer. Okay, so for those of you who would like to follow along, what we first need to do is start with a balanced reaction. It says silver nitrate, which is this right here, reacts with excess sodium chloride to produce 1.3 grams of filtered dried precipitate. So first thing you're going to do is you're going to write your reaction. So I react my silver nitrate with my sodium chloride. I realize this is a double replacement reaction. I go ahead and I produce sodium nitrate and silver chloride. I need to use page 6 in my data book to see which one would form a precipitate. This guy here. Once you have your reaction, you then need to list what you know. So for this problem, our ultimate goal is to determine percent yield. So we need to have an experimental yield and an actual yield, or a calculated theoretical yield. Whenever you are looking for calculated yield, you're going to be calculating that amount out. So we have two values here. We have 2.85 grams of silver nitrate that was reacted in solution of sodium chloride. So I'm going to go ahead and list this here. Okay, and it was produced 1.31 grams of filtered precipitate. Now ask yourself, is that calculated or is that my experimental? So this here is actually from my experiment. It's from the lab. So this is my experimental. We don't need that value right now. Part A says determine the predicted mass of the precipitate. So we are actually looking for the mass of our precipitate. I like to leave a little extra room underneath my reaction just in case I need to list anything else. Let's begin writing our Stoic statement. You're going to start with what you know. I have silver nitrate. So I'm going to start with 2.85 grams of silver nitrate. We now need to convert this into moles, okay? And the way that I do that is I'm going to use molar mass. The molar mass of this is 169.87 grams per mole. In order to cancel out grams, I need to divide by my molar mass, 169.87 grams per mole. From here to here, I have canceled out my grams, and I'm currently left with moles of my silver nitrate. N represents moles, and I'm just going to write silver nitrate. When I have moles, that is an indication that I can now use my mole ratio. This balanced reaction indicates that it is a 1-to-1 ratio. I divide by 1 mole. Remember, ones are invisible in chemistry. A lot of students think that just because there's no coefficient, that indicates a 0. No, if we had a 0 in front of our coefficient, in front of our reactant, that means we would not have any of it. Because anything multiplied by 0 does not exist. Okay, on the top, we have silver chloride. Let's see what we have now. Silver nitrate cancels out with silver nitrate. Moles cancels out with moles. Now from here To here, I have moles of silver chloride, which is moles of my unknown. We are almost there. We are looking for grams. So in order to do that, we need to use molar mass of our precipitate. Calculate that out. That's 143.32 grams per mole. I am now going to multiply 143.32 grams per mole. You always want your unit that you're looking for. In this case, grams would have to be in the numerator. So I need to make sure I end off with grams in the numerator. Silver chloride does not cancel out. Moles cancels out, and I'm left with grams of silver chloride, which is my precipitate. So now from here to here, I have mass of silver chloride. All right, so once we plug that in, I'm going to round my answer off to 3 significant digits. The reason being is because I was given 3, I'm going to end off with 3. So I get 2.40 grams of silver chloride. This is my calculated yield. Okay, percent yield. The formula for percent yield is equal to experimental yield over calculated multiplied by 100. Okay? My experimental yield was given to me in the problem right here. It's 1.31 grams. So let's plug that in. My experimental is 1.31 grams divided by my calculated, which is 2.4 grams multiplied by 100 to give me a percentage. Once I calculate that in, I get 54.5%. So not the best yield. We got about half of what we were looking for, what was expected. Okay, so let's begin gas stoich. In gravimetric stoich, we used molar mass. To convert between mass and moles. So you'll remember I sometimes will draw, not that poorly, but I will draw this saying that if you're going from mass to moles, we use molar mass as a converter because our converter has both grams and moles in it. Converter usually has both. Okay? In gas stoich, if you can think back to the gas unit, we use this thing when we're learning about the ideal gas law in Avogadro's. We used molar volume to convert between volume and moles. Now, a lot of students get confused between molar volume and concentration. So in gravimetric, first of all, it is volume that we're dealing with, volume of a gas. That is important. And we are trying to convert it into moles or vice versa. We use molar volume. Make sure you use the correct units. Molar volume is measured in liters per mole. Do not confuse it with concentration, which is moles per liter. It is the opposite. Okay? Let's do some gas. Oh, let's review some of our molar volumes here. At STP, our molar volume is 22.4 liters per mole. Liters per mole. At SATP, our molar volume is 24.8 liters per mole. At a non-constant temperature and pressure, molar volume will need to be calculated using the ideal gas law constant, okay, which was capital R. R is equal to 8.314 kPa over mole. Okay, we will use this and perform unit analysis to find our molar volume if we have a non-standard temperature and pressure. Let's do an example. For example, if hydrogen and oxygen reacted at 150 kilopascals and 19 degrees Celsius, the molar volume would be what? So, Vm, you're going to begin with your R constant, 8.314 kPa over mole. Okay, so this is an example of finding non-standard molar volume. Remember that the symbol or the variable for molar volume is represented by V lowercase m. You start with your R constant, and then you're going to ask yourself, what units am I trying to keep? And how am I supposed to have these units? I'm supposed to have liters in the numerator and moles in the denominator. So we need to keep these units. We need to cancel out our pressure and our temperature. So the first thing that you should probably do is you need to calculate. I'm going to get rid of my pressure first. We notice that our temperature is given to us in Celsius. Whenever we're working with ideal gas law or anything to do with gases, you need to make sure that your temperature is in Kelvin. To get 19 degrees Celsius into Kelvin, I need to add 273.15 Kelvin. Sorry, not Kelvin, that's the converter. That will give me Kelvin. Okay, I'm going to plug this in, see what we get. Okay, so that's going to give me a temperature of 292.15 Kelvin. This is just simple unit analysis. If I can get one message across to you in Chem 20 is that unit analysis is so universal. We pretty much have used it in every single unit, and it'll be helpful in Chem 30 as well. 150 kilopascals, I'm going to cancel that out by dividing by 150 kilopascals. Kilopascals cancels out with kilopascals. Perfect, we're halfway there. We need to eliminate one more. Here, we have Kelvin in the denominators. In order to get rid of that, I am going to multiply by 292.15 Kelvin. Kelvin and Kelvin cancels out. Look at that. We are left with liters in the numerator and moles in the denominator. Plug that in. I get a molar volume of, let's just do 3 significant digits, 16, actually we'll do 16 liters per mole. And that's it. Pretty simple stuff. Okay, let's move on to an example. Hydrogen gas is produced when sodium is added to water. This is a pretty cool reaction. What mass of sodium is needed to produce 20 liters of hydrogen gas at SATP? Just like every Stoich problem so far that we've done, you need to write a balanced reaction. Without a balanced reaction, we can't really get an idea of what we need and what we need to do. So hydrogen gas is produced when sodium is added to water. Sodium, solid, plus water, and produces hydrogen gas. This is going to be like a single replacement reaction because you have a cation switching places with a cation. So it's going to produce sodium hydroxide. Okay, perhaps it will be better if I draw this reaction like this. So we have HOH. They're kind of connected together like that. The hydrogen and the sodium metal are switching places. Okay, let's label what we have here. We have 20 liters. Let's write it with all the significant digits. 20.0 liters of hydrogen gas at SATP. Woo! At SATP, so that's 24.8 liters per mole. What mass of sodium is needed to produce that 20 liters? So we're looking for grams of sodium. Okay. Once you've listed everything, we can begin Stoich. You need to start with your known. Oh, I forgot. I always forget to do this. You need to balance your reaction. So let's take a look here. We're going to need 2 waters and 2 sodium dioxide, 2 sodiums. Great. You guys can always list your products and reactants if you're having difficulty balancing it. Let's begin our Stoich. We're going to start off with 20 liters. This is my known. You always start with the known. 20 liters of hydrogen gas. You need to convert this into moles. The goal is always to convert it into moles so that we can use the molar ratio. In order to convert this, we are now going to use our molar volume. We are going to divide by 24.8 liters over moles. Liters cancels with liters, and from here to here, we have moles of hydrogen gas, which is our known moles. Once we have reached the known moles, we can then use molar ratio. I am going to divide by 1 mole of hydrogen gas, and we're looking for sodium, so I'm going to multiply by 2 moles of sodium. Let's see what cancels out. Mole cancels out with moles. Hydrogen gas cancels out with hydrogen. So now from here to here, we have moles of sodium. I'm only doing this part to show you what we have. Okay, which is our unknown moles? Now ask yourself, what am I looking for? Liters, grams? I'm looking for grams. So we need to use molar mass to find this. I'm going to list my molar mass. It's 22.99 grams per mole. Okay, so we're going to divide, or sorry, not divide, multiply. 22.99 grams mole. Okay, so let's see what cancels out. Mole cancels out with moles, and I'm left with grams of sodium. Perfect, that's what we are looking for. So once I calculate that, So now from here to here, I have mass of sodium, which is my unknown. Okay, plug that in, and we are going to round it to 3 significant digits. It's going to give me 37.1 grams of sodium. There is my final answer. In order to produce 20 liters of hydrogen gas, I would need to use 37.1 grams of sodium. Okay, nitrogen and hydrogen react to form ammonia. What volume of ammonia is produced when 7.5 kilograms of hydrogen reacts with 450 kilopascals at 800. Okay, what volume of ammonia is produced when 7.5 kilograms of hydrogen reacts with 450 kilopascals at 80 degrees Celsius? First things first, we need to get this set up. Nitrogen gas reacts with hydrogen gas to produce ammonium. Second step that I've been forgetting, balance. 3, 2, yep, that's balanced. Next step is to list your known and your unknown. 7.5 kilograms, that's a lot of hydrogen. And we want to see how much, what volume of ammonium is created. So what volume? We're looking for liters. And then they've given us non-standard temperature and pressure. So we have to find VM. So they've given me 450 kilopascals and 80 degrees Celsius, which I'm gonna convert into kilopascals. Sorry, into 350 point. Okay, so we've got our information listed here. Let's, for the sake of it, start writing the Stoich statement. Some of us will want to convert this right away into grams. So I'm going to do it that way because I know majority of the class prefers to work with grams over kilograms. If you like using the kilograms, then you can go forward with it. This isn't asking us to report our answer in any different form. So if you want to give your answer in kiloliters, you can as well. So this is actually 7,500 grams. So I'm just going to get rid of the 7.5 kilograms because it's the same information and I don't accidentally want to use it twice. 7,500 grams of hydrogen gas. We now need to convert this into moles. And the way that we're going to do that is use molar mass because we're using mass. The molar mass of hydrogen gas is 2.02 grams per mole. So I divide by 2.02 grams per mole. Okay, what's canceling? Grams and grams. I'm not going to do the outline for this question. Once we have moles of our known, we can use molar ratio. Molar ratio. We have 3 moles of hydrogen gas and 2 moles of ammonium. Moles cancels out with moles. Hydrogen cancels out with hydrogen. From there, we are then going to see what we're actually looking for. They want us to calculate liters of a gas. In order to calculate liters of a gas, we need to use molar volume. Okay? But they've given us temperature and pressure. They haven't given us a standard molar volume. So I'm going to go ahead and calculate my molar volume. I'm going to do that calculation underneath here. So my Vm is equal to, I'm going to take my R constant, 8.314 kilopascals, kcal over mole. Let's eliminate our pressure first. So I'm going to divide by 450 kPa. That cancels out, that cancels out. And then I'm going to multiply by my temperature, 353.15 Kelvin. Kelvin and Kelvin cancel out. We're left with liters per mole. That's great. That's units of molar volume. Okay, once we calculate that out, I get a molar volume of approximately 6.5246 liters per mole. Good practice here. You keep at least 4 decimal places, or you use the answer that you got in the calculator when plugging it in for the next calculation. This is an intermediate calculation, so we are not going to round yet. So I'm going to use my molar volume here. 6.5246 liters per mole. Let's see what cancels out. Mole cancels out with moles, and I'm left with liters of ammonium. Great, that's exactly what I was looking for. Please go back and check what you were looking for. Okay, I get a very large answer of 16150 liters. Okay, we need to round this to 2 significant digits because our smallest number that we used in our calculation was 7.5. So let's scroll down. We can't represent this unless we put it into scientific notation. So I'm going to get an answer of 1.6 times 10 to the 1, 2, 3, 4. Positive 4 liters of ammonium. There is my final answer. Okay, you're going to try this one on your own. What volume of oxygen at STP is needed to completely burn 15 grams of methanol? Lucky for you, you have a balanced reaction right there. When you are done, you may unpause and check your answer. Okay, so here we are. We've listed our known and our unknown. Instead of using a question mark, I highly recommend that you do a blank line and with the preferred units, only because students get confused as to what they're looking for. So it's a good way to indicate, yes, I need liters of this. This is what I am looking for. Starting my Stoich statement, I start off with the grams of methanol and use molar mass to convert it into moles. The reason we use molar mass is because we are given mass, and the way to convert mass into moles is to use molar mass. Once I have moles, I used my molar ratio. My molar ratio then converted it into moles of oxygen gas. We are required to find liters. And so because it's a gas and we need to find volume, I need to use molar volume to help me calculate this out. So then I go ahead and multiply it by my molar volume, and it cancels my moles out, and I'm left with liters of oxygen. Again, what I need to look for. Once I calculate that out, I get an answer of 16 liters of oxygen. You may pause if you need extra time here. Okay, let's do one more example, and then you'll try one on your own, and we will be done. An Albertan home is heated with methane. Methane is CH4. A home consumes about 2.00 kiloliters of natural gas during the month of December. What volume of oxygen at SATP is required to burn 2.00 kiloliters of methane measured at 0 degrees Celsius and 120 kilopascals? Okay, let's go ahead and list some of these things. I've already written us a balanced equation. And then from here, we are going to list some things. So what volume of oxygen in SATP? So we're looking for volume of oxygen at SATP, which we know has a molar volume of 24.8 liters per mole. Is required to burn 2.00 kiloliters of methane measured at 0 degrees Celsius and 120 kilopascals. Okay, let's begin off with our known. I'm going to do this one a little bit differently. Because it doesn't say how we should have our volume, we can actually calculate it out into kiloliters, which will make it easier. If you don't like that, you can convert the kiloliters into liters and find liters of oxygen as well. Because it's not specifying, both answers are acceptable. Begin with what we know. 2 kiloliters. Oh, okay, let's start over. 2 kiloliters of methane. We need to convert this into moles. Since we have liters of gas, we need to be using molar volume. The molar volume is measured at 120 kilopascals and 0 degrees Celsius. So you are going to use your R constant to find your molar volume. Okay, so that we're going to start off with our R constant, 8.314 kcal over mole. We need to cancel out our pressure and our temperature. Pressure was, what was our pressure? 120 kilopascals. And we had 0 degrees Celsius, which if we convert into Kelvin is 273.15 Kelvin. Kelvin cancels out with Kelvin. Kilopascals cancels out with kilopascals. Okay, and I get a molar volume of 18.9247 liters per mole. Okay, I'm not going to round. This is an intermediate step. I'm going to go ahead and list this right here. This belongs here. Liters per mole. Okay. So I'm going to divide by 18.924 liters per mole. Liters and liters cancels out, and I currently have kilomoles. That's fine. As long as the base unit is moles, we can then use our mole ratio. So I'm going to divide by 1 mole of methane and multiply by 2 moles of oxygen gas. See what cancels out. Mole cancels out with moles, methane cancels out with methane, and I currently have kilomoles of oxygen. Okay, so we are looking for liters of our oxygen, and that was at SATP conditions. So we are going to use our molar volume, 24.8 liters per mole. Mole cancels out with moles, and we are left with kiloliters of oxygen. Once I plug this in, I round this to 3 significant digits. Yeah, that 0, we're going to let that one slide. It should technically be 0.00 degrees Celsius, but yeah, for the sake of this, trust me, and let's just round it to 3 significant digits. 6.04 kiloliters of oxygen. Fantastic. Last but not least, you're going to try this you-try problem on your own. Once you're done, you can unpause and check your answer. Okay, so let's look at the setup. I listed my known and my unknown. I started off with my known, and liters canceled out with liters once I had found my molar volume. That calculation is located down here. I currently have kilomoles. Then I use my mole ratio to convert my ammonium into my unknown moles. Moles cancels out with moles because we are looking for grams. I used molar mass. We end up with grams, kilograms of our fertilizer ammonium sulfate.